This video provides an overview of the autoflight system in ATR aircraft equipped with glass cockpit. While many functions are similar to those found in legacy aircraft with AFCS cockpit, there are some key differences. Every effort has been made to present the system accurately, but errors may still be present. For information, system failures are not covered in this video. For precise and detailed information, please refer to the Flight Crew Operations Manual, FCOM. If you spot any errors, feel free to share them in the comment sections below. The Autopilot System, or Automatic Flight Control System, AFCS, is made up of the following key components. Two core avionics cabinets, CIC-1 and CIC-2, which control and monitor the autoflight system. One flight guidance and control panel, FGCP, which is used by the pilots to interact with the autoflight system. Two index control panels, ICP, one for each pilot, which are used to set target airspeed, altimeter barometric setting, and instrument approach minima. Two flight mode annunciators, FMA, located at the top of each primary flight display, PFD. Vertical and horizontal flight director bars on each attitude display indicator, ADI, providing lateral and vertical guidance. Three servo actuators, one for each of the primary flight controls, elevator, rudder, and ailerons. One power trim box that interacts with the elevator trim actuator. Two go-around push buttons, one on each power lever. Two Autopilot quick disconnect push buttons, one of each control wheel. Two touch control steering TCS push buttons, one on each control wheel. The CACs receive information from two air data computers, ADC, two attitude and heading reference systems, HSRS, the radio altimeter, nav1 and 2, they receive VOR and ILS localizer, both flight management systems, FMS, and from some other aircraft systems. The autoflight system provides the following functions. 1. Flight director, FD. 2. Autopilot, AP. 3. Automatic pitch trim when the autopilot is engaged. 4. Yaw damper, YD, providing turn coordination. 5. Automatic rudder trim when the yaw damper is engaged. 6. Altitude alert. The autoflight system is powered by the DC Essential Bus, DC Emergency Bus, and DC Standby Bus, which means it can operate with both DC generators inoperative. However, in that case, some systems are lost, including both DME, VOR ILS number 2, GPS number 2, FMS number 2, and ICP number 2. The general rule is that the autopilot shall only be used when the aircraft is at least 1,000 feet above the ground, except during takeoff and approach. After takeoff, the autopilot can be engaged above 100 feet. For approach, the minimum altitude for using the autopilot or flight director is 160 feet. However, during an ILS Category 2 approach, the autopilot can be used down to 80 feet on the radio altimeter. If an air data computer or attitude heading reference system is inoperative, or if both DC generators are inoperative, the autopilot and yaw damper must not be used when the aircraft is below 1,000 feet above the ground, or when the indicated airspeed is below 160 knots. When using nav mode for VOR approach, the use of autopilot or flight director is only allowed when a co-located DME is available, or when DME hold is not selected. This chapter explains the logic and color coding of the flight director modes displayed on the FMA. Lateral modes, such as heading mode and VOR navigation, are shown here, while vertical modes, like indicated airspeed and altitude hold, are shown here. Active modes are displayed in green color, while armed modes are displayed in cyan color. However, the callout is blue. For example, if we are flying in heading select mode with VOR mode armed, the callout is heading select green, VOR blue. The autopilot cross-check and responds with checked. Once the flight director captures the VOR signal and begins to intercept it, the callout is VOR star. The response is checked. A green box will appear for 7 seconds to grab attention. When the flight director is locked on the VOR, the callout is VOR green. The response is checked. Again, a green box will be visible for 7 seconds. Here is another example. We are flying in indicated airspeed, IAS mode, climbing towards a specific altitude. The callout is IAS green, alt cell blue. Checked. Once the flight director begins issuing commands to level off, the callout is alt star. Checked. When the flight director captures the altitude, the callout is alt green. Checked. The flight director's commands are displayed as 2 green bars on the ADI. Note that it is the flight director that issues the commands, while the autopilot simply follows them. When flying manually, your task is to follow those commands, which is accomplished when the small square representing the aircraft's fuselage is precisely at the intersection of the 2 flight director bars. Finally, when a flight director mode is active and you press the push button for that mode for a second time, the flight director reverts to basic mode. For example, if you are climbing in IAS mode and press the IAS push button, the flight director will revert to basic mode, which in this case is pitch hold. The basic modes are explained later. The ATR aircraft operates with 2 different minimum operating speeds, which are defined as a factor of the stall speed. They depend on aircraft weight, flap setting, phase of flight, and atmospheric conditions, normal or icing. The first speed is minimum speed low bank, VMLB, or low bank speed. It limits the bank angle in turns to 15 degrees. The low bank speed is displayed on a PFD as follows. On the right side border of the airspeed tape, as the top of an empty amber band extending down to the stick shaker speed, which is presented by the top of the red band. A low label shown in the lateral mode window on the FMA. 2 green ticks on the 15 degrees bank indication on the ADI. Low bank speeds are used for takeoff, best angle climb, single engine climb, and go around. Minimum speed high bank, VMHB, or high bank speed, limits the bank angle in turns to 27 degrees. High bank speed is 5 to 10 knots higher than low bank speed. It is displayed on the PFD as follows. The low label is absent. 2 green ticks on the 27 degrees bank indication on the ADI. High bank is used for all flight regime except those specified for low bank. The transition between low bank and high bank occurs automatically. Low bank is selected when the indicated airspeed is less than high bank speed or the radio altimeter is below 1000 feet. High bank is selected when the indicated airspeed exceeds high bank speed plus 5 knots and the radio altimeter is above 1100 feet. The Flight Guidance Control Panel, FGCP, serves as the primary interface between the pilot and the autoflight system. The panel is divided into 3 sections, with individual controls for each pilot on either side. The FD push buttons toggle the flight director bars on and off on the associated ADI, although the flight director modes remain active. The course and nav source controls will be explained in the navigation mode chapter. In the center of the panels are controls used by both pilots. The standby push button deactivates all active and armed flight director modes. The heading knob is used to adjust the heading bug on the navigation display and HSI. Pressing the knob resets the heading bug to the aircraft's current heading. The altitude select knob allows you to pre-select the altitude you intend to climb to or descend to. The pre-selected altitude is displayed in cyan on the top of the altimeter on the PFD and as a bug on the altimeter scale. When the aircraft begins climbing or descending towards the selected altitude, altitude select mode is automatically armed. However, if the aircraft is climbing or descending away from the selected altitude, altitude select mode will not be armed. The aircraft is equipped with 2 VOR ILS receivers and 2 flight management systems, FMS. To allow the flight director to determine which navigation source to follow, there are 2 controls. The first is the coupling push button, CPL, which toggles between the left and right sides when pressed. The coupling must always be set to the side of the pilot flying. When the coupling is set to the left side, the flight director will follow the navigation system selected with the navigation source selector on the captain's side. In normal operations, the captain will use FMS number 1 and VOR ILS number 1. When the coupling is set to the right side, the flight director will follow the navigation system selected using the navigation source selector on the first officer's side. In normal operations, the first officer will use FMS number 2 and VOR ILS number 2. During an ILS approach, the flight director will follow the ILS on the coupled side until reaching 1200 feet on the radio altimeter. Below 1200 feet, the flight director will use the average signal from both ILS receivers, a mode known as dual coupling. The coupling selector also determines which air data computer and attitude heading reference system the flight director will receive information from. The left row of push buttons controls the lateral modes, which manage the vertical flight director bar and the ADI. When no lateral modes are active, the flight director defaults to basic mode, either heading hold or roll hold. Heading hold engaged when the bank angle is 6 degrees or less, rolling the aircraft to wings level and maintaining the current heading, regardless of the heading bug's position. If heading data from the HSRS is not available, the system switches to wings level mode instead. Roll hold activates when the bank angle exceeds 6 degrees, maintaining the current bank angle or adjusting to 15 or 27 degrees, depending on whether low bank or high bank is used. The heading push button is used to activate heading select mode. When heading select is active, the flight director turns to and follows the heading bug. If you turn the heading knob more than 180 degrees, the flight director will not reverse the turn but continue the turn in the direction initially selected. In normal operation, heading select mode is used in the following situations. 1. Takeoff. When the aircraft is lined up on the runway, the heading knob is pushed to center the heading bug and the vertical flight director bar. 2. When following radar vectors from air traffic control. 3. When intercepting localizer or VOR radials without using the FMS. 4. During initial phase of a go-around. 5. When you temporarily want to deviate from your flight plan, for example to circumnavigate thunderstorms. 6. When flying visual patterns. En route navigation can be conducted using the FMS, VOR or NDB as the navigation source. When the navigation source is set to FMS and the nav push button is selected, the flight director follows the active flight plan in the associated FMS, engaging lateral navigation, LNAV. However, GPS signals can fail or be jammed. While the FMS has a DME backup, its accuracy is reduced in such cases. If the FMS is compromised, VOR is the preferred alternate. The navigation source is switched to VOR ILS, the correct frequency is tuned and the course is set to the appropriate radial on the HSI. If the VOR lacks a collocated DME, the flight director may overcorrect near the station, requiring the use of heading mode instead. Heading mode is also used when navigating with the ADF. A two-dimensional approach is an instrument approach that provides lateral guidance, but unlike a three-dimensional approach, does not include vertical guidance. Instead, the vertical speed mode is used to manage the descent profile. The types of 2D approaches include LNAV approach, VOR DME approach, VOR approach, NDB approach, localizer or LDA approach, and localizer backcourse approach. An LNAV approach is an RNAV or RNP approach where lateral guidance is provided by the FMS. A VOR-DME approach can be flown either using the VOR receiver and HSI or with LNAV, provided the pilot monitoring cross-checks the VOR on the HSI and confirms the aircraft remains within ±5 degrees on approach course. A VOR approach without a collocated DME cannot be flown using the autoflight system in navigation mode. Without knowing the distance, the flight director cannot calculate the correct heading corrections to intercept and track the VOR radial. Instead, you must use heading mode, or you can use the FMS in LNAV mode, while the pilot monitoring is monitoring the VOR on HSI. An NDB approach can be flown in heading mode using the bearing needle on the HSI as a reference. It can also be flown using LNAV, provided that the pilot monitoring monitors the NDB bearing and confirms the aircraft remains within ±5 degrees on the approach course. A localizer approach can only be flown in localizer mode because the obstacle-sensitive area near the runway is narrower than the 0.3 nautical miles corridor used by the FMS. A localizer-type directional aid approach, LDA, is a localizer-based approach that is not aligned with the runway centerline. The BC push button is used to arm the localizer backcourse mode. A localizer backcourse approach is an instrument approach procedure that utilizes the localizer signal in reverse direction. Here is an example. At Waterloo Regional Airport in Iowa, United States, there is an ILS approach to runway 12 with a frequency of 111.7 MHz and a collocated DME. The approach course is 128 degrees. For runway 30, a localizer backcourse approach is published. This procedure uses the same frequency, 111.7 MHz, as the ILS for runway 12, but the approach track is 308 degrees. However, an important detail not immediately evident on the chart is that when flying a backcourse, the course selector on the HSI must be set to the opposite course, 128 degrees. If the course select is incorrectly set to 308 degrees, the deviation bar on the HSI will reverse, causing it to deflect in the wrong direction and misleading the pilot to steer away from the localizer beam rather than towards it. Warning: never fly a localizer backcourse unless it is certified by the relevant authority. Attempting to improvise your own procedure is unsafe, as the localizer backbeam is not calibrated, and there is no guarantee that the approach meets safety standards. Approach mode is used to select one of the following 3D approaches: ILS approach, LNAV approach, LPV approach. When flying an ILS approach, pressing the approach push button arms both the localizer and the glide slope. The glide slope can only be captured after the localizer is captured. If localizer mode is deselected after the glide slope is captured, the vertical mode will revert to pitch hold. Once the glide slope is captured, altitude select mode is inhibited, allowing you to set the published Goran altitude. When flying an RNAV or RNP approach, the initial modes are LNAV mode and either VNAV or altitude hold mode. Pressing the approach push button arms the vertical flight path, VFP mode. When the aircraft is 2 nautical miles from the final approach fix, VFP becomes active, and the flight director will follow the published vertical profile for the approach. In many ways, VFP functions very similar to an ILS glide slope. When active, altitude select mode is inhibited, and you can set the published govern altitude. Localized performance with vertical guidance, LPV, is an RNP approach providing a level of precision similar to an ILS. This is achieved by utilizing satellite-based augmentation system, SBAS. In North America, it's known as Wide Area Augmentation System, WAAS. In Europe, it is known as EGNOS, in India, Gagan, and in East Asia, MSAS. Ground stations across each area monitor GPS signals and compute a correction signal that is transmitted to a geostationary satellite, which transmits the signal to the aircraft. For example, this is the chart for RNP approach to runway 14 right at Toulouse, France. The EGNOS channel is 57314. The decision height for an ATR category B is 230 feet. In comparison, LNAV now has a decision height of 410 feet, and LNAV a minimum descent height of 460 feet. Note: minima for the 3D approach is given as a decision altitude or height, while minima for a 2D approach is given as minimum descent altitude or height. This type of approach requires installation of additional equipment in the aircraft. When the aircraft is cleared for approach, the approach push button is pressed. This arms L-lock and LGS modes. They behave like an ILS localizer and glide slope. The right row of push buttons is for vertical modes. They control the horizontal flight director bar on the ADI. When no vertical modes are active, the flight director is in pitch hold mode, which means it maintains the aircraft's current pitch altitude. The pitch wheel is used to adjust the pitch target, which is shown by the horizontal flight director bar. The indicated airspeed push button activates IAS hold mode, which is standard vertical mode for takeoff and climb. Standard climb speed is 160 knots for ATR 42 and 170 knots for ATR 72. IAS mode is also used during emergency descent. When IAS mode is active, the flight director commands a pitch that allows the aircraft to capture and maintain the indicated airspeed displayed atop of the airspeed indicator. If the speed is shown in magenta, it is managed by the FMS. If the speed is shown in cyan, it is manually managed by the pilot, who adjusts the speed using the speed target knob on the index control panel. The pilot can switch between automatic and manual control using the Auto Man Select push button. If the aircraft is in level flight, a new target altitude must be selected with the Alt Cell knob before IAS mode is selected. Otherwise, the flight director will revert to Alt Hold. The target indicated airspeed is also indicated with a bug on the airspeed indicator. The color is the same as for the numeric value. The VS push button activates vertical speed hold mode. When VS mode is active, the rate of climb or descent is controlled using the pitch wheel. VS mode is primarily intended for descent, but it can also be used in climb when performance is good and the aircraft is about to level off. If the aircraft is in level flight, a new target altitude must be set using the Alt Cell knob before selecting VS mode. Otherwise, the flight director will revert to Alt Hold. The target vertical speed is displayed with a bug on a vertical speed indicator, and the color matches the numeric value. The VNAV push button activates vertical navigation mode. VNAV was introduced with standard 3 software, so early 600 variants do not have this push button or function unless they have been upgraded. Note, VNAV is only available when LNAV is active. There are 4 VNAV modes, 2 for climb and 2 for descent. The first mode is VNAV IAS. It can be armed before takeoff, but can also be activated in flight during a climb or in level flight to initiate a climb. The purpose of VNAV IAS is to ensure the aircraft does not exceed altitude constraints on standard instrument departure, SID. Some SIDs require the aircraft to cross a waypoint at or below a specific altitude. On this chart, one waypoint must be crossed at or below 6,000 feet, and 2 other waypoints at or below 9,000 feet. VNAV IAS helps manage this. When the aircraft is cleared by air traffic control to climb to a higher altitude than the altitude constraint, and the cleared altitude is set in the alt cell window, the FMS calculates the altitude the aircraft will have when crossing the waypoint. If the aircraft is expected to reach the altitude constraint before the waypoint, the flight director will arm VNAV alt, and the altitude constraint will be displayed in magenta next to alt cell. VNAV alt overrides the altitude set in alt cell, and the flight director will command the aircraft to level off at the assigned altitude. When VNAV alt is active, VNAV IAS is armed. When passing the waypoint, VNAV IAS becomes active again, and the aircraft will resume climbing. Although many ICDs do not have cross at or below altitude constraints, it is considered good operating practice to arm VNAV IAS before every takeoff, when LNAV is used for navigation. Before starting descent, alt cell must be set to an altitude below the aircraft's current altitude. 5 minutes before reaching top of descent, the vertical deviation indicator will appear on the ADI. If the VNAV push button is pressed before the vertical deviation indicator is visible, VNAV VS mode will activate, and the aircraft will begin descending at the rate of 1500 feet per minute. If the VNAV push button is pressed when the vertical deviation indicator is visible, VNAV path mode is activated. When the VNAV push button is pressed before reaching top of descent, the FMS calculates a new vertical path from the aircraft's current position to the first waypoint with an altitude constraint. As a result, the vertical path will be shallower than the standard 3-degree descent until reaching the waypoint with the altitude constraint. When the VNAV push button is pressed after passing the top of descent, the FMS commands a 5.5-degree descent path until it intercepts the nominal 3-degree path. This results in a descent rate of about 2,800 feet per minute, which can make speed control difficult. Therefore, if you overshoot the top of descent, a better option is to use VS mode set a descent rate of 1800 to 2000 feet per minute until capturing the normal descent profile. The Alt push button activates altitude hold mode. It is rarely used because Alt select mode is automatically armed and climbing or descending towards the selected altitude. However, altitude hold is useful when air traffic control instructs you to level off at an altitude near your current altitude during a climb or descent. When one of the go around push buttons is pressed, the flight director switches to heading hold and go around mode. The pitch command is based on the flap setting and provides a minimum safe pitch up attitude. Once the landing gear is selected up, the procedure is to select heading select mode and IAS mode. When the missed approach procedure in the FMS is confirmed, LNAV mode is engaged. If LNAV was already engaged when the go around push button was pressed, LNAV remains active to guide the missed approach procedure. The touch control steering TCS push button on the backside of the control wheel enables the pilot to take temporary manual control of the aircraft without disconnecting the autopilot. A green TCS label is displayed on FMA when used. The TCS can be used to adjust pitch and roll in basic mode and adjust rate of climb or descent in VS mode. The Autopilot and Yaw Damper push buttons are used to engage and disengage the respective functions. The Yaw Damper enhances passenger comfort and provides automatic rudder trim. It is engaged when the landing gear is detected and is switched off before landing. It is crucial to turn off the Yaw Damper before landing due to its automatic rudder trim function. If you forget to disconnect the Yaw Damper, the rudder trim will counteract your rudder inputs during landing. A good operational practice is to turn off the Yaw Damper when the autopilot is disengaged and the aircraft is below 500 feet on the radio altimeter. The autopilot follows the commands from the flight director and provides automatic pitch trim. The autopilot will only operate when the Yaw Damper is engaged. The engagement sequence is as follows. When the autopilot is selected on, both the autopilot and Yaw Damper engage. When the autopilot is selected off, the autopilot disengages, but the Yaw Damper remains on. When the Yaw Damper is selected off, both the autopilot and Yaw Damper disengage. The autopilot can be manually disconnected by pressing the autopilot push button, using the quick disconnect button on the control wheel, pressing one of the go-around push buttons on the power levers, activating pitch trim, or applying excessive force on the flight controls. The autopilot will also disconnect automatically if there is a discrepancy between the air data computers, the attitude heading reference systems, or due to some other system failures. A full description of these conditions is provided in the FCOM. The speed hold push button is not active. It was intended to provide an auto power capability for ILS Category 3 approaches. However, no airline has opted to include this function, as the development and certification costs outweigh the operational benefits. The altitude alert is an oral C chord lasting for 1 second. It is triggered in the following situations. 1. When the aircraft passes 1000 feet before reaching the pre-selected altitude during climb or descent. 2. When the aircraft deviates more than 250 feet from the pre-selected altitude. The altimeter box will flash amber when the aircraft's altitude is between 1000 feet and 250 feet of the pre-selected altitude. When LNAV is in use and the aircraft is 1 minute from top of descent, the vertical track alert VTA is triggered by flashing the selected altitude and its bug and the magenta V on top of the vertical deviation indicator. The alert ends when altitude select has been modified by the crew. When the vertical gradient will change at a waypoint, the vertical path change alert VPCA is triggered by flashing the vertical deviation indicator and the magenta vertical speed and its bug, 10 seconds before the pitch change will take place. The flight path angle protection system was introduced with the standard 3.1 software. The purpose is to prevent the aircraft from stopping climbing after takeoff or go around, or when encountering significant downdrafts. The flight path angle protection system is available in the following situations. 1. In indicated airspeed mode for 180 seconds after liftoff. 2. In go-around mode for 180 seconds when the radio altimeter is less than 500 feet. 3. In VNAV IAS mode. This is a good reason for arming VNAV IAS before every takeoff. When the flight path angle protection system is active, the autoflight system controls pitch directly. If the flight path angle protection system is active for more than 20 seconds and the speed is less than high bank speed, pitch hold mode is activated, together with 3-click audio alert. This gives the flight crew time to assess the situation and select the best sequence of actions. For example, selecting altitude hold to retrieve acceleration capability. The purpose of the high-speed protection is to prevent the aircraft from exceeding the maximum operating speed. It is available when the autopilot is engaged, and VNAV PAV, VNAV VS, VS, Alt-star or pitch hold modes are engaged in descent with flaps retracted or flaps 15. When the airspeed is approaching maximum operating speed, the autoflight system takes over and reduces the descent rate, possibly down to 0. When the high-speed protection has been active for more than 3 or 6 seconds, depending on flaps configuration, a 3-click audio alert is triggered together with a reduced speed label on the FMA. The purpose of the low speed protection is to prevent the aircraft speed from decreasing significantly below minimum operating speed. When active, the autoflight system takes over pitch guidance and alerts the flight crew. Low speed protection is available when the autopilot is engaged, and VNAV Alt-star, VS or pitch hold modes are engaged in climb with flaps retracted or flaps 15. If the airspeed approaches the minimum operating speed, the autoflight system starts to control pitch, and 3 seconds later, monitor speed is displayed on the FMA. When the vertical speed reaches 0 feet per minute, while low speed protection is active, the active vertical mode is replaced by protection level mode, maintaining a vertical speed of 0 feet per minute. The purpose of the complementary low-speed alerting is to alert the flight crew that the aircraft speed decreases significantly below minimum operating speed. We mean OPS. The alert is available in flight above 80 feet and consists of 3-click audio and a speed message on the FMA. However, the autoflight system does not intervene. With flap 0 or flap 15 and protection level is not engaged, the alert is triggered when the indicated airspeed decreases to minimum operating speed minus 5 knots. With landing flaps and protection level is not engaged, the alert is triggered when the indicated airspeed decreases to minimum operating airspeed minus 3 knots. When the protection level is active, the alert is triggered when the indicated airspeed decreases to minimum operating airspeed plus 1 knot. This concludes the video about the autoflight system in ATR aircraft with glass cockpit. Please note that some software variants may not include all functions described here. Furthermore, the functions have not been explained in full detail. Always refer to FCOM or the specific aircraft you are flying for accurate information. Thank you for watching.